All right, so a couple of points that are coming up in homework and also relating to what I wanted to talk about with differential equations today. I've taken it for granted, but I haven't proved to you, why does this expression, which we've been computing for the last day and a half, why does this expression give the parenthetically unique, question mark, solution of the differential equation x dot equals ax? So I sort of took this for granted based on the diagonal case, when we said if you uncouple the system of equations, it turns into stuff you know from basic calculus. But I really want, I really want to address this a bit more. So how would you check that this is a solution to that? Take the derivative. So let's just check. If I take, if x of t is e to the ta x naught, what is the derivative with respect to t? So I'm going to emphasize that now by writing it sort of in classical style for a minute. So to answer that, what have you got to figure out? Well, it's a matrix of functions, right? So the question is exactly what Cameron's saying. What do you think the derivative of e to the ta should be?
A.
How did you decide to put the a on the left side? I want it on the right. Be careful now, you've got commutativity issues. Matrices don't commute. Or is it e to the ta a?
We don't really have it.
Should I just stick them both? Stick on both sides.
I think it's the second one, right?
Yeah. Equal opportunity for all matrices.
Right, equal. So, every day you toss a coin and randomly decide which way you're going to write it?
So that's
Works for me.
so far.
I'm pretty sure it's the second, but I don't really know why.
We did have something where there wasn't a
Well, alright, so the first comment here, folks, is they're the same. So why are they the same? Well, what is e to the ta? It's given by an infinite series, which is?
A to the k over kx.
You should not forget Mr. T.
Sorry, t a to the k. K0 and then to b.
So if I wanted to multiply by an a, seems like I could just distribute it, as long as it certainly works for finite sums, right?
The t will go out and
And this is just a to the k plus 1, and I can then pull the a out on the other side. It really doesn't, right? A commutes with a to the k. Alright, so now if somebody wants to be pedantic, Daniel's missing, so does somebody want to substitute for him? Yeah. Just because it commutes up for a finite sum, can you make it work for an infinite sum?
That's the limit of the finite sums.
So for those of you who have taken 3100 or 2410, it should follow easily from uniform convergence, so I invite you to think about that.
Uniform convergence of what? You see the
Of the series. So this series converges uniformly for t in any closed interval. So I'm not going to belabor this, but I am going to use it again today. So you're not responsible for this. It takes some real analysis down the road. Some of you are. And it's similarly, if it's a fact that follows from uniform convergence again, that you can differentiate a power series term by term, and when you do that, you get the derivative of the power series. So that is supposedly proved in 3100. It's definitely proved in 2410. It follows from uniform convergence that we can differentiate term by term. So if I take d dt of the sum, you can pull the d dt inside, and then the sum of the derivatives. So this is like saying if you have an integral, you can take the limit of the integral as long as you have uniform convergence. It's the same sort of argument. So differentiation term by term means you take the derivative with respect to t, and then what happens? Whoops, no, that's all right.
T k minus 1, k minus 1 factorial.
T to the k minus 1 over k minus 1 factorial. Now I'm not going to put k equals 0 anymore, because for k is 0 this is gone. So I'm going to start with k equal 1. And a to the k. Ugh, I don't like that. What do?
K minus 1 times a.
Pull out an a, right? So this now is a times the sum with everybody having an exponent a k minus 1. And because k starts at 1, I can re-index k minus 1 starts from 0. So this is the same thing as writing with a new letter if you prefer, but I'm going to be lazy and just use k still. It now goes from 0 to infinity. So this is a e to the ta. Okay? So it follows that if I take the derivative of this, I get a times this, which is what I want. Everybody see that? This is constant. X naught's constant. So if I take d dt of this, I get a e to the ta x naught, which is a times x of t. Okay? So we're done.
So if we took the derivative like 100 times, would we get t to the k minus 100 over k minus 100 x factorial a to the k minus 100 times a?
Yeah, I'd rather not. I would just rather repeat this. Right? This is a constant, so if you take the derivative again, it's a constant times the derivative, so inductively you're going to pick out an a each time, just like you would with the scalars. All right, but we've checked it's a solution. But why couldn't Will come up with a different solution? Right? Just because I have a solution, I mean, I know you want to be good physicists and physicists missing too. You want to be good physicists and engineers here and not mathematicians. So if somebody tells you, it's the only one, you'll be happy with that. that somebody in the room ought to want to know why couldn't there be some other solution? Volunteering? No. No one's volunteering?
I'll volunteer. Why is no other solution?
Why unique solution? And similarly, because I want to use this stuff to argue in 2 minutes that sine and cosine are the only solutions of the simple harmonic motion equation. I don't want to just say, well, I trust the physicists, they told me those are the only solutions. So David, even though he's not volunteering, secretly in his head he has some other solution in mind. And how do we show him he's made a mistake and it really was the same solution?
Let's suppose that's it.
So suppose we had some presumably other solution x of t. Let's call it y of t. So what do we know? We know that y satisfies the differential equation, that its derivative is a times y, but we're not convinced that y is of this form. We're not convinced that it's y to be that. Oh, I guess it has the same initial condition too. Does anybody have an idea? This is a trick. Consider z of t, which is not the difference, that I don't know what to do with the difference. But here's what I'm going to do. I'm going to multiply by e to the negative ta times y. So now what is e to the minus ta?
It's the inverse of the
It's the inverse. So you're proving in homework, in number 17, you're showing that e to the minus ta is the inverse of the matrix e to the ta.
Is that 9.3?
Yes. I do not want you to do it by taking the infinite series definition and trying to multiply infinite series together, even though Reese wants to do it that way.
Get it?
I don't want him to do it that way. So the hint for that, which I thought the book had in it, but apparently somebody ignored, consider ddt of e to the minus ta times e to ta.
Are we allowed to do that limit?
Yes, you're absolutely allowed to use the lemma.
Is it equal to 0?
That's what you want.
And there is a
Shh. All right, so using this fact, what is ddt of z of t? Z of t is all the way over there. That's not very nice. ddt of e to the negative ta y of t.
Negative.
So first of all, how am I going to do a product? Thank you. Product. Be careful about order of things. So I'm going to do derivative of respect to t of this, and I guess Cameron's telling me that the negative by the chain rule comes out as a negative. Or you can think of this as e to the t times the matrix negative a. Agreed? And then negative comes out. Negative a. Okay, times y of t plus
E to the negative ta minus y dot of t, which equals
Now it's important that they commute, isn't it?
Yes.
Sort of like it was important earlier on last semester that matrices, the inverse had to work on both sides. We talked about how one side was important for existence and one side was important for uniqueness. So what happens? Well, we're done, right? We have minus a e to the ta plus a, plus e to the ta a, all times y of t, and this is 0 matrix. So what does this do? 0 vector. So z of t is constant. What? So whatever it is at time 0, it's that for all t. And what is z naught? Y naught. And what's y naught? It's x naught. Therefore, e to the negative ta times y of t is x naught for all t. And we're done. So y has to be of the form that we had originally guessed. Therefore, that's the only solution. Very powerful, actually, as I will now show you. Any questions on that? So, application. I'm going to do a special case, then I'm going to do a general case here. So, the general solution of y double dot plus k squared y equals 0 is constant times cosine kt plus constant times sine kt. So remember we actually turned this into a first order differential equation. We did something like this yesterday. How do we turn this into a first order? Differential equation. What did we do yesterday when I gave you a couple of second order things?
Define what's make an x that is equal to y. Like the x of t equals y dot, y double dot.
No, you're up too high. Y
Y
and y dot. Right, and then you end up with a matrix that gives you x dot is going to be y dot, y double dot. Which is something times y, y dot. So we did this yesterday for a couple of examples, right? So you get a 0, 1, and a minus k squared here. No. Yes. Minus k squared, 0. Is that right? Y double dot is minus k squared y. Y double dot is minus k squared y plus no y dots. So all we have to do is figure out how to exponentiate that matrix. And I'm not going to take the time to go through it all because I have other things to do. And so notice that I'll leave the general case to the reader. I guess you're not reading. Okay. Now you have to do it. But the case where k is 1, we did yesterday. It says looker. K equals 1 is essentially the matrix we did, the rotation matrix we had yesterday. Except I had it with the negative here and the positive here.
the opposite direction.
Yeah, just rotating the other way. So we saw yesterday that exponentiating this matrix gave us a rotation matrix through angle t, except now it's going to be the negative t. So you're going to have cosine t, negative sine t, sine t, cosine t. So we did this yesterday explicitly. And if you keep track of the k squared here, you are in fact going to end up with kts.
Is that k equals 1 or k equals 0?
1. Right? Y double dot plus y equals 0. Okay, right? I want k equal 1. So in fact, you get that x of t is cosine t, negative sine t, sine t, cosine t, x naught, initial vector. What's the initial vector? Well, it's going to be y at time 0 and y dot at time 0. So this is y of t, y dot of t. So if you read off the first coordinate, you see exactly that you get this solution, which is exactly what we used when we dropped Jonathan through the earth a few weeks ago. But what we've proved is this is the unique solution, right? Because of this uniqueness fact for first order equations. Any questions on this? For future reference, I'm going to give you a more general version of this that's actually stated in the book. And we can actually use it as an application here of some of our schmancy fancy stuff. So, more generally, suppose you have constants a naught to a n minus 1, and we consider the differential equation. So it's going to be nth order differential equation. Y nth derivative. So I'm not going to use dots now. I don't know how to put n dots. Plus a n minus 1, n minus first derivative of y, plus down to a1 times y, plus a naught equals 0. So I'm interested in a function that's n times differentiable that satisfies this equation where the a's are constants. I'm going to try to make it look like a first order. So here, so the statement is going to be, then, the solutions form a blank dimensional subspace of the functions that are n times continuously differentiable. So remember we talked about this last semester. Cn are the functions that are n times continuously differentiable, and we proved that that was a vector space. Whatever interval you're on, I don't care. Now what dimension do you think? How many degrees of freedom in the solutions? N, right? Here we had second order, 2 dimension. First order, 1 dimension. So surely this is n. So this is really cool. So this linear algebra ties together with the matrix exponential stuff, and you can actually prove some non-obvious fact about solutions of differential equations. So Ken already had the idea, just like we did here and just like we did yesterday. I'm going to convert this into a first order differential equation. So I'm going to introduce a new variable, x, which is going to be what? Where does it live?
-1.
Well, let's write it down and then we'll decide where it lives. What do I put? And then the derivative's up to n minus 1. So this is now a curve in R n minus 1. So this is going to be in R n minus 1 for each t. So we're looking for a curve instead of R2, what we had here, we're looking at Rn minus 1. Whoa, something's not right.
We're doing with R2.
Oh, it's Rn, folks.
Yeah.
Why do I listen to you? This is 0, 1, up to n minus 1. Should never listen to you guys. So it's a curve in Rn whose tangent vector is given by some linear vector field, Ax. Again, now what's my A? This one's sort of fun now. Can you see it in your head, or do I have to write it out? So you have to write out the derivative of this. So the derivative of this is going to be y prime. How do I get y prime with this? 0, 1, and then none of the others.
Okay.
The next slot is y double prime. 0, 0, 1.
So you're going to have a column of zeros in the first column.
Yeah.
And then
Now be careful. What's the last row?
the second to last one is 0 all the way to a 1.
Okay,
Then the
fine.
last
And then the last one,
Your negative a's.
I'm solving for yn, the nth derivative. So I have to put all this stuff on the other side.
So we did all the.
Oh, wait a minute. Wait. I screwed up. Hang on. This is not a subspace if A naught is here. Sorry, my fault. Hang on. So this should have been A0 is the problem. Right, I wanted the subscript going with the derivative. This was the 0th derivative. So I screwed this up, I apologize. It should have been A1 y prime plus A naught y. Sorry, my fault. All right. So now what happens? When I take yn and put all this stuff on the other side,
Negative a naught, negative a1.
and then the very last one here is negative a n minus 1. And let's check. This was supposed to be n by n. This is n. Now that I have it correct. Yeah, sorry. So this was wrong before. So we can compute the solution by exponentiating that matrix and multiplying it by the initial x vector. So what do I need for data for x naught?
Can I ask a question?
Uh-huh.
So that diagonal has a 0 on it?
The diagonals are all zeros except at the very bottom. So this is the diagonal.
Wait, that's fine.
And then at the bottom one, it's not 0. So that's generalizing this one. But at the bottom one, we did have a 0 here, Jonathan, because I had no coefficient of y dot there.
Fine.
Hello.
Hello.
Well, we had a few people trying to substitute for you, but it didn't work. So what data do I need for x naught? I need to know all of these guys at time 0. Right? So we're going to get the solution depends on how many parameters here? Well, we're in Rn. So the initial vector is in Rn on the n parameters a naught to an minus 1. So in other words, to have a solution of an nth degree, nth order differential equation, you need the function and its first n minus 1 derivatives at a starting point. And then you get a unique solution. Now, you didn't stop and ask me, and I'm quite appreciative that you didn't, but you didn't stop and ask me why this was a two-dimensional vector space in this case. How do I know that this function and this function are linearly independent? Well, of course they are.
Power series, because one's formed out of even functions and one out
Okay,
of
one's even, one's odd. Cosine vanishes at pi over 2, sine does not. Sine vanishes at 0, cosine does not, so they cannot be, one function can't be a multiple of the other. Any number of ways to see it. But it's not so obvious here that when I write out the general solution from this formula, that I'm going to get n linearly independent solutions. So let's think for a second about this. Why do these span an n-dimensional subspace of the vector space of n times differentiable functions? So I actually have to look at what we've got here for a little bit. Yes, sir?
Would it come somewhat from the matrix A we have?
Mm-hmm. Somewhat.
Like, I'm just kind of thinking the rows that have the ones wouldn't be able to be covered for by the other ones.
Yeah.
Since each row that's not the bottom one has a unique one for that row.
Well, are you trying to argue that this matrix A is non-singular or something? I don't think that's true.
What can't?
I mean, it's not A, that it's really the exponential that's going to matter. If A naught, notice, if A naught is 0, which could happen, I could have a differential equation with that term not there, then I would have a column of zeros and the rank of A would be smaller. But that's still not going to affect the statement. It's still, this statement is still true. Or am I missing what you were thinking, Dennis?
No, it's sort of I don't understand what I was thinking.
Well, then how do you expect me to?
So an n-dimensional subspace of Cn, wouldn't that be all of Cn?
No. This is an infinite dimensional vector space. N times differentiable functions.
Ah, okay.
Very infinite dimensional. Remember, it has all the polynomials of all degrees in it. All right, no, so it's a little more subtle than that.
Write these out. Like we did.
Well, I am certainly not prepared to tell you what a closed form formula is for e to the TA. I am not competent to do that. Maybe I had an oracle called on in the last class. Maybe the oracle can do it, but I can't.
Should we go back to the infinite sum?
Do some,
But we, since it's lower triangular, maybe we
Well, okay, so
conversions.
let's think about what this looks like for a minute. So x of t is going to look like y of t, y prime of t, and so on, is e to the TA times x naught. Now, trying to think about the argument I wanted to do for this.
Actually, it could be b values in that case.
So, I don't think I hadn't actually planned to do this.
So we're trying to show why the A's form a subspace, right?
Yeah, no, okay, I'm okay. Yeah, well, no, we know they form a subspace. Not the A's, the solutions form a subspace. Because this is a linear, I didn't say it, but this is a linear homogeneous system, linear homogeneous equation. So if you take any solution of this and you scalar multiply it, it's still a solution. And if you add two solutions because derivatives are linear, you again get a solution. So it's a subspace. The question is why it's n-dimensional.
Okay.
So let's think about what this looks like. If I'm interested in e to the ta times the vector x naught. I'm interested here in y of t. So, if I'm interested in y of t, where does it come from this expression? Comes from the first row. And then multiplying by x naught. Okay? So let's say that the first entry, I'm going to label these guys. Q naught of t times the first coordinate here. So let's just say C naught times Q naught plus C1 times Q1 up to Cn minus 1 Qn minus 1, where the Q's, Qi are the entries of the first row of E to the TA. Okay? What do I want to argue? I want to argue that these are linearly independent. So whenever you compute this matrix exponential, I mean, look at what we got in this example. We got cosine t and sine t. But more generally, I want to argue that Q naught to Qn minus 1 are linearly independent. In the vector space of n times differential functions. Declaration.
So
Gabe's falling asleep.
all the C's will be 0. Why?
So suppose C naught, suppose you're at constants, so that these added up to the 0 function. Right?
This is 0 function.
It's 0 for every t. So for all t, this is expression evaluated at t is 0. If you have the
We will show C naught equals C1 equals Cn minus 1 equals 0.
One of the courses you advanced, it becomes required to show that C naught.
So if you have a function of t that's 0 for all t, what can you do with it?
Add it to itself.
What else can you do with it?
But you use it on itself again.
What are we talking about? The vector space of what kind of functions?
Oh, you can differentiate it.
I can differentiate it. All the derivatives have the same relation. Because the derivative of the 0 function is the 0 function.
So then we get from C naught, that'd be Q1
second.
So you're gonna do it break down now?
So what do we get?
That y prime, is that, now we just know something about y prime.
I feel like we're on the,
Yeah,
we're on the
define
second
the
row.
second
and
row
it's-
is
There you
T
go.
naught.
So, yeah, you're on the right track here. So this is saying that the zero vector is what you get when you take the first row of this matrix and multiply it by these scalars.
The second row.
So the first equation was the first row.
Right.
But now we have y prime is also 0.
Well, they're all 0.
So this is going to, if you continue this way, you get it's true for all derivatives. So you're going to have not only the first row here, but then y prime is also going to be 0, and so forth. So you're going to end up with all of these being 0. Right? So you're going to have not just the first row with these constants giving you 0, but all of them, all these rows are going to give you 0, which is going to say that the 0 vector is e to the ta times this vector of constants. Right? You're going to have not only y of t is 0 for these constants, but all of the derivatives will be by differentiating. So this will all turn out to be the 0
Only if you
vector.
suppose that one of them.
The first, right. Starting with the first one, if y of t is 0 for those constants, then all the derivatives are going to be 0.
This is a silly question, but could you have chosen any of them to start with and like integrate it up for the other ones?
Don't go there.
Yeah.
Don't go there. But we've already proved this is invertible. So c is 0.
Can we write that in homework? We already proved it. So.
Right, you're doing it for homework. So. Okay. So I have one last topic I want to do before we go back to pure linear algebra tomorrow. So this is one of many beautiful connections between differential equations and chapter 8. So I want to connect this.
That depends on e to the ta being invertible.
Yeah.
Whoever does
Is it-
chapter 8.
Is it invertible if a0?
Yes. It's always invertible. The inverse is e to the minus ta.
Okay.
Yeah. It's always invertible. I mean, yeah. So suppose you have a vector field, say a nice C1 vector. C1 vector field on Rn. Do R3 if it makes you feel better. You can take a differential equation, call that vector field capital F. Consider the flow of this vector field. So you dealt with this in a homework problem, and I made some brief reference to it here. And this is going to be what Math 4700 is all about, by the way, for those of you heading that way. The flow is, here you are in space, and there's vectors everywhere, whatever the vector field's doing. The flow says, put yourself somewhere in here. That's not a good color. Put yourself somewhere in here and follow the yellow brick vector field.
Go with
Go with the flow. So the curve is going to be start at a point x and follow the vector field as your velocity vector at each point. So phi t of x is the curve that starts at x and follows with its tangent vector. So the derivative with respect to t, the tangent vector to the curve, is going to be the vector field at the point you're at. So you guys have done this, you've considered this for homework with the closed flow line problem. Here's what I want to now, so we've been talking about if the vector field is linear. This is what we've just been doing the last 3 days. If the vector field is given by ax, then the flow is given by e to the ta times where we start. So you actually have examples of this from what we've been doing for the last 2 days. So here's the problem I want to pose. Here you are in Rn. Start with a region omega. Take every point in omega and let it flow by this vector field. So sitting in Rn, I have my vector field. Start at any point and follow where it flows for time t. So for any x in the region, it flows for time t to position phi t of x. This point flows over here. This point flows over there. So at time t, what have I got?
A blob that's been spread out.
I've got a different blob, right? Wherever it's moved to, I now have a blob, which is phi t of omega.
Could it connect into two different blobs, or will it always stay connected? I feel like it'd be connected.
This is actually, phi t is actually smooth as your vector field is, and it has an inverse, which is flow backwards. So by continuity, you can't create pieces and then uncreate them. What do you think I want to ask?
Change in volume.
Change in volume. How does this flow distort the volume?
That can be like normal bag.
No, but I'm doing a general vector field.
Oh.
The norm isn't the right thing, actually, but you'll see in a second. So the natural question is, what is d dt of v of t, say at t equals 0? So as you start to flow, at what rate is the volume changing? Any intuition for this? Imagine the vector field's radial and you started with a ball.
You're adding
What are you doing when you flow by a radial vector field? What are you doing to the ball?
you're adding another
You're
adding another surface to it.
You're making it get bigger, and the rate at which the volume changes instantaneously is the what?
The surface area.
The surface area of the boundary. Well, what if the vector field isn't pointing outward, but is just pointing tangent to the boundary? Does the volume change? As you flow, you just turn around, you don't grow, right? So what do you think?
It's like the opposite of work.
The rate of change of the volume should be what? It should relate the vector field and the boundary of the region.
Can we cheat if we read the book?
No, then you should keep
Is it
quiet.
flux?
It's the flux. How much is the vector field flowing across the boundary of omega? That's what's making it spread. So it's going to be the integral over the boundary of omega of f dot n. This is in n-1 dimensions, but we can write it all out with differential forms, no problem. What does this remind you of? Flux of f integrated over the boundary is integral over the inside of div. And that's the theorem, that the rate at which the volume changes as you flow by the vector field is given by integrating the divergence of the vector field over the volume. So you're doing basically, this is intuitive here. There's a direct argument given in the book, which I'm not going to do, but I could do it in 10 minutes, but I think you're too impatient now. Based on basically just saying, pull back the volume form, integrate over omega. This is what, if you flow for time t, pull back the volume form from this object, that's integrating the pullback here, that's the change of variables theorem. And then you want to do ddt of this. And I do want to get this one punchline in. What problem did you do earlier this semester that relates a derivative of an integral? This depends on the variable there.
Differentiating that.
Differentiate under the integral sign. Yes. And what is ddt of the pullback? Well, that must have something to do with saying ddt of the flow is the vector field. So this must bring in differentiating the vector field. And I'm not going to continue at this point, but it turns out that the answer, if you compute it at t equals 0, you're going to get exactly df1 wedge dx2 wedge up to dxn plus all the terms up to differentiating the last component of the vector field. And if you think about this, this is going to do the x1 derivative of f1 up to the nth derivative of xn, and that's going to be the divergence. So if you're interested in this, after the semester's over, read the page of proof in the book, or half a page of proof. All right, section 9 for tomorrow. Be well.